I'd like to do another example involving Taylor's inequality. So let's find the degree n Taylor polynomial for the function e to the x at x equals 0. And then let's use that answer to approximate e squared. So here is my answer. First, I need to find the degree n Taylor polynomial. So the degree n Taylor polynomial is y, which is a0 plus a1 x minus 0 up to an x minus 0 to the n, where ak is given by the kth derivative evaluated at my center, in this case 0, divided by k factorial. In this example, my function is e to the x. It's very easy to take derivatives of e to the x. Derivatives of e to the x are just themselves. So the kth derivative of my function is just e to the x, and if I plug in 0, I get 1. So in this case, ak is just going to be 1 over k factorial. So I get 1 over 0 factorial plus 1 over 1 factorial x. The next term will be 1 over 2 factorial x squared. Next term, 1 over 3 factorial x cubed, and so on, until I get to 1 over n factorial x to the n. That is a very nice Taylor polynomial. It's the Taylor polynomial for e to the x at x equals 0. So I have my Taylor polynomial, and I'd like to use it to approximate e squared. So e squared, I'm going to approximate by just plugging in x equals 2. So if I plug in x equals 2, I get 1 plus 2 over 1 factorial plus 2 squared over 2 factorial plus 2 cubed over 3 factorial, and so on until I get to 2 to the n over n factorial. Now, how good of an approximation is this? That's the question you should ask every time you're approximating. If you have any kind of approximation, the first question you should ask is, how good is it? Am I close or am I far away? Well, that's what Taylor's inequality can tell us. I'll remind you of the statement of the theorem once again. It says your error when using the Taylor polynomial to approximate your function is less than m over n plus 1 factorial c minus a to the n plus 1, and that's where m satisfies this condition. The n plus first derivative of your function has to be less than or equal to m for values of x that satisfy this. So in this example, the error is less than or equal to m, and then n, in this case, is just n, so I'm going to leave that as n plus 1 factorial. C is equal to 2, and a is equal to 0, so this is going to be 2 to the n plus 1 power, where m satisfies some condition. Now, the n plus first derivative of e to the x is e to the x. So e to the x is less than or equal to m, and that has to be true for values of x that are less than or equal to 2. If you think about the graph of e to the x, it grows very fast, exponential growth, super fast growth. the graph of e to the x looks like this. So if I'm on the interval from -2 to 2, that's what this condition says here. My values of x have to be in between -2 and 2. The highest that the function can be on this interval is right here, the value e squared. Now e is 2.71828 something. So e squared is less than 3 squared. So 9 is, up here maybe. I'm going to take m to be 9. So m will always be bigger than e to the x on the interval from -2 to 2. So my error is less than or equal to 9 times 2 to the n plus 1 power over n plus 1 factorial. Now, if n gets bigger and bigger and bigger, 2 to the n plus 1 is going to be smaller than n plus 1 factorial. So you could think about it like this. This is equal to 9, and then I've got n plus 1 copies of 2. So 2 times 2 times 2, multiply a bunch of 2's together. I got n plus 1 2's. And on the bottom, I have n plus 1 factorial. That's the same thing as like 1 times 2 times 3, all the way up until I get to n plus 1. If you think about it for a moment, the bigger n is, the more the denominator, the more this bottom part will be larger than the top part. Why? Well, if you think about it, only the first number, 1, is smaller than 2. After that, in the factorial, all of these numbers I'm multiplying together are bigger than 2. So the bottom gets bigger much faster than the top. In other words, what I'm trying to say is the limit as n goes to infinity of 9 times 2 to the n plus 1 over n plus 1 factorial is equal to 0. That means the bigger n is, the better my approximation will be. This is the error bound. This says my error is less than or equal to this. And this quantity has limit 0. So if I take n to be larger and larger and larger, my error gets smaller and smaller and smaller. All right, excellent.